So how's everybody today? A good crowd. You used to say, if you act enthusiastic, you'll be enthusiastic. So how's everybody today? Good, okay. Well, thanks for coming. You've got me for about a half hour, 45 minutes or so, and we're going to talk a little bit more about wireless gauging. Now, I'm George Schuetz. I work for Mar Federal in Providence, Rhode Island. I think I can make it through the presentation. We had a big party for me yesterday because my marketing team arranged for a 40th anniversary party working for Mars, so I'll try and make it through the presentation, but it was just a wild evening last night based on that. But anyways, I'm going to try and make this a little bit of fun. We're going to talk a little bit of history, things that are going on now, and maybe we'll set the stage for what's going to happen in the future with all types of the different types of gauges that are coming along. So like I said, we've got a lot of things to talk about. We're going to talk about a different type of an industrial revolution, which I think is going on. But in order to do that, we have to set the stage of where that's coming from. So we're going to see and learn about the way that we used to do quality control in manufacturing, talk about data collection and its history. I've kind of been around the whole data collection time frame, so I think I can add some insight to that. Then we'll talk about some of the wireless things that are changing the way that people collect data and how that's being integrated into a lot of gauges, but it's also being integrated into a lot of different processes. And then I think there's a lot of benefits that are going to come out of this seamless data collection, and maybe that's going to set the stage for another industrial revolution in the future. So we don't have to wait till the end to ask any questions. If you have any questions, as I say anything, feel free to ask. If you think I'm lying about something, let me know, and we'll try and correct it. Okay? But I think going digital is a way of changing the manufacturing in the world today. I had the word digitize. I couldn't say the first word up there, so I took it out and called it going digital because it's a lot easier to say. But I think, between the technology and the internet, it's really having a big influence on manufacturing and also quality control. And the past industrial revolution has been based on getting things done faster. I think in the future it's going to be data is the real industrial revolution of the future. And the data is going to be coming from lots of different measuring technologies with the plan of making things more productive, giving better production speeds, flexibilities, and you'll see they'll be able to make things individually a lot faster and probably more economical. So what set up industrial revolutions? Well, I think we're getting ready to go into maybe the fourth phase of the industrial revolution. But what were these phases? Well, they started out where you had to harness power to do things. So between water power and steam engine, we're able to turn things now. And that was really the first start of the Industrial Revolution. And then you add electric power, and you got to a phase of doing mass production. And I think we're kind of just winding down the third phase of the Industrial Revolution processes that we've gone through, and that's the computerization and advances in product quality. And now we can kind of talk about this whole phase of where we've been and where we're going in the terms of advances in data collection and how wireless technology might help us in the future. But really, before there was the start of data collection, the old way of measuring in the beginning of the Industrial Revolution was send everything through the quality department. You build a batch of parts, You send them to the inspector, they would measure them. If they were good parts, they'd be sent to the customer. If they were bad, they'd be reworked or scrapped. And that quality department was really the king of the hill, so to speak, because they were the ones that determined whether that part was good or bad. But they really didn't know what was happening and why it wasn't good or bad. So while they were important, they really didn't know too much about the things that were happening along the line of manufacturing. And really that whole process is reactive by nature. It prevents the shipment of bad parts, but it doesn't prevent good parts or bad parts from being made in the future. The cost of labor and so forth, as you can imagine, are high of that because you're duplicating parts, you're wasting time making the measurements, and it gets expensive doing that. And the whole process of making the parts, bringing them to a quality control room to have somebody else measure them is really it's not a very productive way because there's a lag time between the manufacturing and understanding of what caused that error to be made. So even if you did find the bad parts, by the time you went ahead and told somebody about it, and they could have made another 1,000 parts, and which again is costly to everybody involved. So that go, no-go method was very similar to the go, no-go method of the gauges that people were using at the time. Call them go, no-go gauges, call them fixed limit gauges, but they're a way of only telling us whether that part was good or bad. And at the time, that was a pretty good thing. It got the Industrial Revolution going. It made parts interchangeable. It was a quick way for a user or an operator to tell whether that part was good or bad. So really that was kind of the first stage of getting some of those quality control processes right to the point of manufacture. They were consistent, they were portable, they were easy to use, but often for every part that was manufactured, there was a go, no-go master required for that. So I think we all know that the Industrial Revolution might have started with weapons or guns or something like that. And so if you can figure for each part that was manufactured, there was a separate go, no-go gauge for that. They had to be measured somehow, checked, tracked, evaluated, and that became a pretty expensive process. They were pretty easy to use. You know, if the part goes through it, it's good. If not, it's not so good. Relatively economical to make, but very costly over time to maintain. And again, they don't tell you too much. They tell you whether the part is good or bad, but it doesn't tell you what's going on with the process, because nobody's keeping track of how many were a little bit tighter going through the gauge or might have been looser or not. So they were a good way of getting things measured at the point of manufacture, but they didn't give the users that much information. Then probably, you know, in the 30s and 40s and 50s, people realized that with a little bit of math, and maybe if they had the opportunity to collect some data, you might be able to use that information to make your processes a little bit better. That's where the idea of process control came along. It developed a system to track the good or bad parts, using things like pre-control and post-control to put that right at the point of manufacturing. And they used to do that whether the part was good or bad, but now if you can measure the data, plot the data, you can start to get an idea of where your process is going and maybe do some things to uncover what's wrong with it to produce bad parts from being measured. And that not only helps you prevent bad parts from being measured, but there's some other things that maybe data can do for you. Besides monitoring the process, there's probably people who want documentation for the parts were measured. Maybe you can do some things with statistics. Maybe you can get your tooling checked out to make sure that you're not wearing your tools out. You can check the calibration of the machine. So, there's lots of ways that data can be used as part of the whole process as not only manufacturing parts, but also letting us know whether the whole process is good or bad. So I think, the whole idea is if you can know a little bit more about the data, that gives you a little bit more knowledge about the whole process. And the whole idea is, I think, if you have that knowledge, you can record it, and then you can start to learn from it. And that's, again, that was the start of the whole quality assurance process, something that started in the 50s and 60s. Statistics was a branch of mathematics long before variable gauging come along, but the idea of putting those two things together started to give putting a lot more power in the hands of the process engineers out on the shop floor. And the availability of that information, the variable data, gave people very clear indications of what was happening with the process. So it was a revolution in the way people manufactured parts. So we said that the quality control people were the kings of the hill, but now that people on the shop floor realized that they could do something with this knowledge, I think some of the manufacturing people, the process people, started to embrace the use of knowledge. So SPC became very widely used in the 60s and 70s, came for use for process control. People started using pre-control limits. I mean, I remember even starting when I was working, we had charts that we put on the machine tools, checking off little X's and O's, whether those parts were good or bad, where the process was going, and they were used on the shop floor as a way of monitoring the process, all in an effort to prevent bad parts from being made. So the concept of collecting data and then using no-go and no-go gauges started to change into the idea of using variable gauges, gauges with dial indicators, gauges with comparators, calipers and micrometers. These were gauges that not only told the user whether the part was good or bad, but also the fact that, is it a little bit bigger than the last one or smaller than the last one? So now you can tell where between those tolerances that part fell. Now when you start recording those numbers and you start putting them in charts where you can break the charts down into very minute elements, you can get a really good idea of what the process is doing. So variable gauges in today's world are hand tools, calipers, micrometers. They have the scale built into them, so you can get an idea of how large or how small the part is. And then there's other variable gauges that use an outside standard for telling whether the part is larger or smaller than the master. Those are usually a little bit faster and easier to use than a caliper, and they also provide higher accuracy for variable data. So there's lots of ways to collect data, and depending on the application, one might be chosen over the other. So at first people had to, like I said, go to a chart, write all this information now, and there's been studies that have been done that kind of show how good or how bad that collection of data process was. And thanks to our friends at Starrett, they've done some studies on this, that typically for 500 people trying to make a measurement and record that value, you're going to get 26 of them are probably going to be either written down wrong, a number is transposed. So 5% of the data could be wrong in that manual writing process. That's time consuming, it's repetitive, And usually for the operators, it's really not a fun thing to do. So now you have to try and get people to write things down. Something typically that maybe the machine operator might not want to do. And then in the 80s, people started to use computers on the shop floor. Computers started to become more economical, or microprocessors were out there. So it was the ability to make data and get it easier, make it easy to use. But still the data had to be manually entered into the computer. So they had to go to a keyboard, enter those values in there, and still we've got a faster way. You don't have to write them down, calculate them all out. Now you're just using a keyboard to enter the values in there, let the computer make all the analysis. You get rid of all those math errors, but still, you still have errors in recording. Maybe you improve the process to 1%, but still, people have to go to a keyboard, they have to use it, it becomes repetitive, and still, I don't think it's a fun thing to do. And at the time, there was really no industrial standard for sharing data. I remember when we introduced a digital product back in the early 80s, it was really the first successful digital indicator. It was a great thing because people weren't writing or reading the needles anymore of a dial indicator. They had a digital value in front of them. It had tolerances built into them. But the first thing people wanted was they wanted a way of collecting the data from that indicator. And at the time, there was really no, it was a new technology. There was no way of getting information from these new digital products out there. So at the time, there was a number of different, not standards, there was a few company standards. So we had our own little protocol for collecting data. All the digital companies had their own different protocols. So it was getting easier to collect data. It was hard to collect data from different companies. So it was better. Data collection was something that was realized, but it was kind of hard to get that digital information into something. So people realized it, and then people started doing standards, RS-232 and all those other standards came along to make it easier for people to collect data. So that was, I think, a real major improvement in collecting data for quality. People can wire things together. They were starting to go digital. It provided a nice way to put information virtually without the operator being involved. A lot easier, a lot more widely used. And by doing that, the improvement in accuracy of the recorded values was dramatic. It's almost no errors because whatever's displayed on the unit can be collected in the computer. There's nothing to write down. You have to take time to go to a keyboard, so it's saving time. And now, to the operator, collecting data is almost no different than measuring the part. It becomes easy. It starts to become a little bit more fun for them to do things. But of course, what happens? When something becomes easy, people want more of it. So now people are collecting data out of everything, and there's not only just one dimension to be checked, there's a whole bunch of dimensions to be checked and multiple things to be done. And so now data is multiplying out there. When the gauges are multiplying to collect data, it becomes kind of a snowballing effect because data is important, it's easy to be done, and it can be collected now. So now you can get multiple gauges with multiple transducers on there, checking multiple diameters all at the same time. But what happens? You start to get a cable required for each unit. The cables break. They can get tangled. They can interfere with the measuring process. And and there's a way of getting all those transducers into a computer. There's probably some hardware required to do that, so it becomes expensive. It's a great thing, it's easy to do, but the act of getting there can be a little bit cumbersome and costly to do that. But people realize how valuable that really is. Besides trying to make multiple things at one time, which is, requires lots of cables, sometimes you can't bring the gauge, bring the part to the gauge. Big aircraft engine parts or tank parts or whatever the parts are, it's tough to bring that part to a gauge. So you would want to have a long wire or something attached to a portable gauge to be able to make that measurement. So those cables break, they pull out of the back, the cables could be a safety issue. So that can be a challenge too for people who want to collect data on large parts. So a short time ago, there was a technology breakthrough with Bluetooth and other types of technologies where through an add-on module, you can take a standard gauge, make it a wireless type of data collection system where you have a proprietary transmitter which is attached to the gauge, usually by a little cable. There's a proprietary receiver, again attached to the computer by a cable. There's software for data management, and each one of those things was a pretty costly piece of equipment to put that system together. But it did a great job. It allowed for people to collect data without having all those cables involved. It kind of made it a little bit more transparent, but still they had this module that you had to tie onto your various gauges. So again, that step helped ensure data-free data collection. It made moving the gauges more portable. It cleaned up the cable nest that you might have out there. Though you're paying a little bit more for that freedom. You're paying for the transmitter and the receiver. And sometimes those add-on boxes made a little bit of an ergonomic error for some of the users in terms of their placement, the cabling, and so forth. A great step forward, but maybe there's something better. So the next step that was taken is people are starting to integrate wireless technology into the gauges and lots of different applications. Wireless technology is becoming easier to use, and that the cost of it is going down. So by building the transmitter into the indicating device or into the hand tool, it frees up any add-on modules. It's just like making a measurement with a standard caliper. It's transparent for the operator to use, so it's really no additional steps that he has to go through. And most of the equipment out there displays for the user whether that transmission was made or not. So it's really easy for the operator to start collecting data. And I think the biggest benefit to a lot of users is that it's a lot less expensive than some of the other items that we or other people sell out there, because you don't have the costly add-on modules. The cost of wireless technology is really the same cost as standard product out there. And I think that's really going to be a key to going wireless in the future. So all these tools that are out there now have taken that technology, you combine it with some powerful digital indicators, with the versatile calipers, so you get great value, they're secure, they're easy to use, it's transparent to the operator, you get good range. There's a lot of benefits to building the wireless technology into today's hand tools. What's that technology is based on? It's based on something that's in the industry. It's called ANT Plus now. And this was a technology that was wrapped around and developed for the medical industry. For medical applications, you want something that's very reliable. You want something that's low power. You want something that can work in a reasonably good range. So it's almost like a personal network that, of wireless technology that can be used locally and is at a very low cost. So it's by employing this technology into the digital indicators and calipers today, you can get good, reliable data collection. It's fast, batteries last a long time, and it's an easy way for companies to implement wireless technology. I think reliability is the biggest issue that people want in data collection, because they want it to work and they want it to know that it's going to work every time. So this technology is very simple to use. It's low cost. It uses a receiver that looks like a USB stick. You can get lots of different channels within a receiver, so you can do multiple tools to it. You can have many indicators attached to a simple gauging program that runs in Excel. You can collect the information all at the same time. And there's no crosstalk between the various ways of collecting data. So it's a good, reliable system that makes data collection easy. So within that system, there's lots of different ways to collect data, and it's really making it transparent to the operator. You can have systems where there's a single gauge making a single measurement. You can have multiple gauges using them in sequence, and the system will keep track of each gauge, know when it's being measured, and put the data in the right spot. And you can have a gauge with multiple wireless transmitters and collect all that data simultaneously. So lots of ways of collecting data, and all the operator does is use the gauge the way they normally did, and it's again transparent for the operator to use. So by having this personal network or personal process control network, the operator takes the part. It could be in the gauge, it could be off the gauge. He can make his measurement to check how good it is. There's process control programs that are built into the machine tool that can collect that information, do the process control, do the tool offsets, all with the same hand tools that the operator has been used to using during his measuring process. So now with that process control, you can start predicting tool life, you can do calibration of the machine tool, and you can prevent bad parts from being manufactured. It's all free, and it's all part of the standard price of a normal hand tool. So I think that basically data collection is almost becoming free to the users now. It's something that's part of the measuring process. People are going to expect that. People want data, and I think they're going to be looking forward to getting data from not only the gauges, but a lot of things in the future, and trying to tie them all together. And that's where that next revolution is. We're going to be able, and all the people involved are going to be able to take that information and do a lot more with that information available to them. Again, because that knowledge can be important to them. And I think transparency is the key to all that knowledge. So that's where the next generation of the Industrial Revolution is going to go to. It's going to be the network factory. I think as you walk around the IMTS, there's lots of companies out there starting to implement that process, tying the manufacturing data with what's happening in the plant, taking into account things from the outside as well, putting more intelligence in the machines, and understanding what's coming down the line. And so it's all tied together, giving the company a lot more strength with its flexible production, giving them more competitive strength. They can start doing individual production, making small batches or one part at a time at the same cost they might do with mass production. And it sets up a very competitive and innovative business model, all coming from getting information. So we'll see that by collecting this information, we really got the Industrial Revolution #4 tied down. We're automating manufacturing. The person at the machine tool is sending information back to the machine tool. He's sending information about the quality of part that is being collected. It's something that can be looked at both locally. You send it out to the cloud. The parent company in a different country can look at that information to see what's going on. And at the same time, that information can be looked at locally for preventative maintenance. And all those things are going to be networked together, and it all comes down to collecting data in a very easy manner. So it starts out simple. It started out with collecting data with a wire. It was a little bit hard, but now we can collect data that's easy for the operator, that's transparent. It provides the benefit of a personal network. It's no more harder for him to do, and that data is available for everybody to use to get a global picture of what's going on. So that's what I basically wanted to do. I just wanted to show you today that we've all participated, I think, in the next generation of the Industrial Revolution, that we started collecting data. With quality control, we started to monitor the process. We're improving the process. We're collecting data. But now with some of the technologies that are out there, we can make that technology almost free, transparent to the user, and easy for them to get a step closer to the next generation of data monitoring. So that's what I want to talk about today. Any questions?
What kind of range are you you talked about this IMTS system.
Mm-hmm.
It's one, there's still low data rates. I'm curious about how low is that? And then two, is that going to be compatible with other systems that you may have in your factory, with ERP or some kind of production planning, and integrate with those?
Well, it's the data rates are slow. I mean, we're talking 8 to 16 times a second, so it's not very fast. But it's typically for hand tools, it's adequate. You can do dynamic things a little bit faster in the gauge itself, and then once say a dynamic max mode or something, you can locally collect that data fast, and then when the measurement's done, send it out. So you don't need the high speed in the wireless data transmission. You have that done on a kind of a local basis. Okay. Was there a second part of that?
The second part was how does it interface with?
Well, everything is going to. We transfer the information through a stick into the computer, so it just goes into we provide a means of getting data into the computer, either into a Excel spreadsheet, a Microsoft type of thing, through a virtual COM port to go into somebody else's information. So we get the data in, and then there's a lot of ways to get that data shared to other places. Yeah.
So what kind of range do these transmitters support?
The range that we work on we have personal networks, so we're talking a 12-meter type of distance, relatively small. So the concept is that a user can have a workbench of tools in front of him. He has his personal network. He knows what parts he's making. You pick the part. You know what measurements you're going to make in sequence. All that data is collected just like you would normally be doing.
How is that sequence illustrated?
Well, through some of the tools that we provide, we would normally put into Excel, okay? And within our tools, we have ways to drop it into one cell, what cell to go into, how many rows across, how many columns down, and you create a little routine that follows that whole path. So you can create a chart for the part. You can create some GR&R test studies and have those forms filled out all automatically. and a very low-cost manner of doing that. You don't need a very complex gauging program to do those things.
Did you expect that to know which part of the component to measure what?
Well, yeah, I mean, you know, one way of doing that is to you set up an Excel file to when you begin it, it goes to the first location. You can have a picture up there to lead the operator through that gauging sequence, and it will fill in all those charts for you automatically. Mm-hmm.
What about non-contact gauging, like vision systems or something like that? Do you guys have anything beyond contact gauging?
Well, we sell vision systems, yes, but yep.
Still operating the same thing?
Well, I mean, with those, I mean, our vision systems would be a standalone dimensional measuring system, not something that's inline or something. So already the computer is there collecting data as part of the measuring process. So it's not quite the same application, I don't think. Okay. Good. Well, thanks for coming up.